Exercise 1102 looks at various trig identities. The first one is the reciprocal ratios. So we've got three new ratios to learn. There's cosecant or cosec, there's secant or just sec, and cotangent. So let's look at what they are. So cosec theta, look at the third letter of each one, S, C, T. They relate to the ones we've already got. S relates to sine, C relates to cosine, T relates to tan. That's your little clue of which one to use. So cosecant, or cosec theta, is the same as 1 over sine theta. So that third letter is your clue that it's sine. So where sine is the opposite over the hypotenuse, this is going to be the hypotenuse over the opposite. It's been flipped upside down. Secant is 1 over cos. So we say sec theta equals 1 over cos theta. So cos theta is adjacent over hypotenuse, so that's going to be hypotenuse over adjacent. I don't tend to use these. I tend to just work out what cos is and then flip it. So I don't memorize those. So cotangent, or cot theta is equal to 1 over tan theta. So where tan is opposite over adjacent, that's going to be adjacent over opposite. So let's look at some examples of how to use that. So in this one, given sine theta is equal to -5/13, find the values of cos theta, cosec theta, cot theta, and sec theta. So the first thing to think about in this question is which quadrant you're in. So because sine is negative, we can draw out all stations to central. They're all positive there, sine is positive here. So down here, it means that we're negative down here for sine. So our angle theta is going to be somewhere between 180 and 360, or technically it could be -0 to 180, remember? But I like to think of it for now, in this purpose, as just being in the third and fourth quadrants. That's enough. So the first step in solving a problem like this is actually just to draw a triangle. Now, we know that we're in the third or the fourth quadrant, so there may actually be more than one answer. So just choose either angle. It really doesn't matter which one, and call it theta. Now, theta's not going to be an acute angle, but that doesn't actually matter. This still works just as well, because what we're looking at is if, for example, it was this angle, we're looking just at this angle here as our theta. So we can still draw a right-angled triangle in this quadrant. So that angle to the x-axis, the related angle there, is what I'm really thinking about here. Now, if this is my theta, then my sine is -5/13. Now, don't worry about the negative at this point. If this is our angle, then the side opposite will mark as 5, and the hypotenuse will mark as 13. So opposite over hypotenuse. The negative will work out in terms of which quadrant we're in. Now, to find the adjacent side, we just do a bit of Pythagoras' theorem. So 13 squared minus 5 squared, and that gives us 12. Okay, once we take that square root. So the adjacent side is 12. Now we can use that to find out our answers. Now, if we're in the third quadrant, and often these examples will actually give you more of a clue about which quadrant they're in. So for example, they might tell you that cos theta is positive, in which case you're definitely in the fourth quadrant. Sine negative and cos positive would have to be in the fourth quadrant. Now, this question hasn't said that, so I'm actually going to give two sets of answers, one for the third quadrant and one for the fourth quadrant. So in the third quadrant, cos theta is going to be negative. So negative, and then just 12 and 13 adjacent over the hypotenuse. So cosec Now cosec can also be written as CSC as well, okay? So cosec theta. Now remember, that's 1 on sine. I kind of like writing it as the whole word, because then that third letter is that one. But it basically means we're flipped upside down. So it's still going to be negative. It's going to be the same as sine. It's just going to be flipped upside down. So negative 13 on 5 for cosec. For cot theta, in the third quadrant, that's going to be positive. Okay, and it's cot is 1 over tan. So what I do is I work out tan. So tan would be 5 on 12, so I flip it. So 12 over 5. And lastly, sec. So for sec theta, I work out cos first, which I've already done, and I flip it. So that'll be negative 13 on 12. Now, pause the video here and have a go at the same thing for the fourth quadrant before I do it. Okay, so let's go. So we're in the fourth quadrant, so cos will be positive, cosec will be the same as sine, so that'll be negative. I might just put that negative there now. Tan is normally negative there, so cot will be negative. Cos is normally positive, so sec will be positive. Now let's just have a look. Our numbers will actually be exactly the same as what they were here. It's still, cos is still going to be the adjacent over the hypotenuse, and sec is still going to be cos flipped upside down. The only difference there is the negatives are different. Cosec is 1 over sine, so that's just this one flipped upside down again. So that maintains that negative there. Cot is 1 over tan, so tan again was 5 on 12, so 12 over 5. So we're going to look at the complementary angle results. Now, this is spelled with an E, not an I, and I is, if you pay someone a compliment, you spell that with an I. This is with an E. In year 7, you learned about complementary angles. You learned that complementary angles add to 90 degrees. You would have also learned supplementary angles add to 180, but here we're looking at the 90 degrees because complementary. So if this angle is theta, and this is a right angle here, based on the angle sum of a triangle, if that's 90, those two have to add to 90, so this angle here becomes 90 minus theta. I've labelled these angles as A, B, and C. So of course the opposite side has the lowercase letter. So here's capital A, this is lowercase a. Here's capital B, this is lowercase b, capital C, so lowercase c. Now what we're going to do on this page is find all of the trig ratios for that triangle. Now I'm just going to do the first couple. So sine theta is going to be the opposite over the hypotenuse. So that's going to be A over C. Now, pause the video and do down to cot theta, and then start the video again. So cos theta will be B over C, because this is our angle. So B over C, tan theta A over B. Sec theta is 1 over cos, remember the third letter, so find cos and flip it, so C over B. Now if any of these were negative, then you'd see something happening there as well, but for all of this we're just assuming right now that we've just got a standard right angled triangle, so we are in the first quadrant. Okay, so cosec, third letter is S, so 1 over sine, so flip sine upside down. And cot is 1 over tan, so tan flipped upside down. Okay, so that was focusing on this angle. Now we're going to do exactly the same thing, but focus on this angle up here. So we're going to find each of these ratios. So sine of 90 minus theta based on this angle is the opposite over the hypotenuse, so B over C. Now, pause the video, have a go yourself, see if you can finish off these. So you should get for cos A over C. For tan of this angle, B over A. So sec of course, is cos flipped upside down, so that's C over A. Cosec is sine flipped upside down, so that's C over B. And cot is tan flipped upside down, so that's A over B. Now, what I'd like you to do now is have a look at all of those results and look for the ones that are the same, because there are some that will always be the same. Okay, so I'm about to show you the results. I just wanted to give you longer if you hadn't paused your video yet. Here they are. Now, it looks like a lot to memorize, but there's no memorization necessary. Have a look at the names of them. This is sine, S-I-N, short for sine, S-I-N-E, and cos is short for cosine, or the complement of sine. That co means complementary. So cosine, sine, they are complementary, so this rule will work. Tangent, cotangent, so the complement of tan, the rule works. So these two, of course, are the same, these two are the same, and these two are the same. We've got second and cosecant, so the complement of second. So these are complementary to each other. So the name of those ratios gives you those results. So here are two examples that use these results. So the first one is to simplify sec 32 minus cosec 58. Now we can simplify this much more easily if they're the same, so either both cosec or both sec. So I'm going to change this second one to sec. I could go either way. Because this is the complement of sec, then that would be equal to sec of 90 minus 58. So take off the co and you got a 90 minus instead. Now 90 minus 58 is actually 32. And a lot of these questions, that's exactly what you're going to get. You're going to get something that simplifies down quite nicely. If you wanted to check this in a calculator, by the way, you'd go 1 over cos 32 minus 1 over sine 58. But these are obviously the same, so that's equal to 0. Now, what you see here is the 32 and the 58, they add to 90. And that's a big clue as well, and we can actually use that. So in the second example, given sine 3m equals cos 5m minus 14, there are two ways you could do it. We can use the 90 minus either way around. So if I was going to use the 90 minus, I'd do the 90 minus 3m. So I'd say that sine 3m is equal to cos of 90 minus 3m. So we get 90 minus 3m is equal to 5m minus 14 because they're now both cos. So 90 minus 3m equals 5m minus 14. Now another way you could do it is to say if you add these you get 90 because of the complementary angles. So you could say 3m plus 5m minus 14 equals 90 degrees. I prefer this. They are the same. You can see that's just got the minus 3m over the other side, but they're both the same. Now we know how to solve that quite easily. 3m and 5m make 8m. Let's actually just add that 14 to the other side, so that's 104. So dividing by 8, I get m is equal to 13. Okay, so we've just got a few trig identities to look at. The first one is the tangent identity, and I've mentioned it several times now. Now, here's a bit of a proof. So here we know that sine theta, here's our theta, A over C. And we know that cos theta equals B over C. So if we look at sine theta over cos theta, so that's A over C for sine, divided by cos, which is B over C. Now I have mentioned before when the denominators are the same, the answer is just going to be A over B, but let's just do that for working that we change divide to times and we flip the second fraction. And then we can see that the C's cancel out. And we do get A over B and A over B is obviously equal to tan theta. So there's our proof. So I'm just going to do two examples that use that result. So the first one is to simplify cosec theta times cos theta. So one little trick you can do with this type of question is just turn everything to be in terms of sine and cos. So instead of cosec, that's 1 over sine, third letter S. So sine theta times cos theta. Now that is cos over sine if I multiply, so cos theta over sine theta. Now that's just tan upside down. That's the same as 1 over tan theta, and we know that 1 over tan theta is equal to cot theta. Here's a second example where we have to prove this. Now, when you get one like this, the layout is quite important. Firstly, choose the more complicated side to start with. So the left-hand side here is more complicated than the right-hand side. So we're going to write left-hand side equals. That's our layout. We must write that. And we write the left-hand side first. Then change everything to be in terms of sine and cos. So we've already got sine there. Sec is the same as 1 over cos, third letter C. And that equals sine theta over cos theta. And that is our tangent identity. That is equal to tan theta. And we need to also write equals left-hand side. Many years ago, they used to also write QED. A lot of people read that as quite easily done, but it's actually Latin, and it means the thing that I was asked to prove, I've proved. It's kind of a little bit of a, you know, I'm proud of myself, I've done this, I've achieved it, you didn't think I could do it, and I have, and that's what QED means. People don't tend to write it now, but I often do if it's a really hard one. If I have had a lot of trouble and I got there in the end, it's like I'm feeling proud of myself that I did it. So I do write that QED sometimes. So we have 3 more identities to go, and these are the Pythagorean identities. In reality, it's one identity, but we can see it work for other things as well. So firstly, if we look at our unit circle, so our radius is 1, this side is x, and this side is y. From that, we can very clearly use Pythagoras' theorem to say that x squared plus y squared equals 1, which is the equation of the whole circle. Every single point on this circle has that equation. But we also know that x is equal to cos. So that's the same as saying cos squared of theta plus sine squared of theta equals 1. And that rule there is used a lot in trigonometry. It's a fantastically useful rule. Now, we can also adapt this rule. I'll just put a box around that one because it's so important. So this is the rule when I said there's only one, but we can change it to some other forms as well. So if I just write down that identity again, and then what I'm going to do is I'm going to divide all of those terms by cos squared theta. So cos squared theta, cos squared theta, cos squared theta. And let's have a look and see what we've got. So cos squared theta over cos squared theta is 1. We know sine over cos is tan, so that's the same as tan squared theta. And 1 over cos squared, we want third letter to be c, so sec squared theta. Another really important rule. Now, one thing that people use to remember this is 1 with a tan is sexy. Now, this rule is it comes up a huge amount. When we do calculus, we're going to be using this rule as well there. So it is well worth remembering it. So 1 with a tan is sexy is the way to remember it. I personally don't like tans, but it's a nice way to remember it. I do hear people saying a man with a tan is sexy. I prefer to say 1 with a tan is sexy. So that's another great rule. And the third identity that we get here is when we divide everything by sine squared theta. So I've divided each thing by sine squared theta. Now cos over sine, we just saw before that that is equal to cot in our previous example. It's 1 over tan, it's tan flipped upside down. So that one is cot squared theta plus sine over sine is just 1. And 1 over sine, third letter s, so that's cosec squared theta. Now, often you will actually see that written the other way around as 1 plus cot squared theta equals cosec squared theta. And we have a very similar way to remember it. 1 with a coat is cozy. So that's how you can remember that one. So those three identities are very, very useful identities and well worth memorizing. The cos squared plus sine squared is pretty easy to remember, but the other two not so much. But if you can remember 1 with a tan is sexy and 1 with a coat is cozy, that will help you remember them. Okay, in this example, we've got a couple of choices of how we could do it. But the easiest way for this particular one is actually just to write everything in terms of sine and cos. So what we're showing is that the sum of cosec squared and sec squared is actually equal to the product of cosec squared and sec squared. Let's start with our left-hand side. So our left-hand side is cosec squared theta plus sec squared theta. Now I'm just going to write them in terms of sine and cos. I could have used those later two identities, but they don't actually help very much here. They may have helped better if we'd started with the right hand side. So this cosec is the same as 1 over sine squared theta plus sec squared is 1 over cos squared theta. Now if I want to add those, I need a common denominator, so this has to be multiplied by cos squared on cos squared, and this has to be multiplied by sine squared on sine squared. So this one numerator becomes cos squared theta, this one's numerator becomes sine squared theta, and I now have a common denominator of sine squared theta cos squared theta. Now that numerator, that's that first identity, cos squared plus sine squared actually equals 1. So that's 1 over sine squared theta cos squared theta. So my square doesn't look much like a square, let's just fix that. Now, 1 over sine squared is the same as cosec squared theta, and that's multiplied by 1 over cos squared, which is sec squared theta, and that does equal our right-hand side. So I'm going to do that one again, starting with the right-hand side. So the right-hand side was sec squared theta times cosec squared theta. Now, sec squared is the same as 1 plus tan squared theta, and that's multiplied by cosec, which is the same as 1 plus cot squared theta. So remember, 1 with a coat is cozy, 1 with a tan is sexy. Now, if I expand that out, I've got 1 times 1 is 1, 1 times cot is plus cot squared theta, tan squared times 1 is tan squared theta, plus tan squared times cot squared, just have to fit it down here, tan squared theta times cot squared theta. Now remember, cot is the same as 1 over tan, so this whole thing here actually just equals 1. So that's the same as 1 plus, I'm going to put the tan squared next, plus this next, that's 1, plus the cot squared. And now I'm just going to use those identities again. I know that 1 plus tan squared is sec squared, so this here is sec squared theta. And 1 plus cot squared, well, that's cosec squared theta. And that is equal to my left-hand side, so equals left-hand side. So you can see either of those methods are completely fine. If you tried to use this identity and start with the left-hand side, it does get a little bit complicated. You'd have to reverse these steps. So going from here to here, where you have to factorize them, to think of changing 1 to tan squared, cot squared, that's really hard. It's really difficult to do that. Whenever you try any one of these types of proofs, if you get a bit stuck starting from one side, then just start from the other side. Or in an exam, you can even kind of start from the top and the bottom and work back towards the middle. sometimes people get to like this line and they don't realize that they're actually there, and it's so close. So if you get to that line and you're like, I have no idea what to do next, well, write the right hand side because you know that's what it's supposed to equal. So there are a few ways to sort of cheat in an exam with these. Okay, in this final example, we're actually going to look back at parametric equations, which we've already talked about in a previous chapter. You've already seen this, but it's really relevant to do it again right now in terms of what we've just learned. So we have to eliminate theta from this pair of parametric equations, and then we have to describe the graph. Now, if you do remember from parametrics, you may already know the answer to that, but let's have a look at it again. So the trick here is to square them and add them. So we want to know what x squared plus y squared is equal to. So x squared is 25 cos squared theta plus y squared, which is 25 sine squared theta. Now I'm going to factor out the 25. So I've got cos squared theta plus sine squared theta. Now we know that cos squared plus sine squared equals 1. So that just equals 25. So our resulting equation is x squared plus y squared equals 5 squared. And we've seen that before. To describe that, it's quite simply a circle with its center at the origin and a radius equal to 5.